pending requests. And somebody gave, yes, I think Andras made it pretty clear he wouldn't do it. I'm not going to twist his arm any further. Somebody also mentioned that breaking into smaller groups would be fun, and that's a good idea. And of course, there's different ways you can break into smaller groups. They were starting to suggest random assignments. I remember when I was a kid, you used to do second captain, first pick. So we could get 3 captains, and then you choose. Solve that problems with you. Anyway, so this is going to happen somehow in the next 12 hours or so. But now we have Ahmad
Abdi. Yeah. Thanks, Bruce, for the invitation. So thank you, everyone, for coming. I know it's a bit late in the afternoon, but I'm going to try to keep it short. So what I'm going to talk about is packing odd T-joints with at most 2 terminals. So let's get started. Let me just talk about the theme of the problem I'm working on. So let's say, the theme falls under packing and covering problem. So what are those problems? For those that were in the session right before now, in the discussion session, they already know what the problem is, but let me recap it for everyone. So you give me a finite set of objects, and then you build a whole bunch of subsets on top of that finite set. So you give me a family of subsets of E, and let's call that curly C. And the big question is, how many disjoint members of C can we find? Or in other words, how many members can we pack? So this is often how you refer to the problem. How many members can we pack? And one way to, so we're trying to maximize this number. One easy way to find an upper bound for this number is via the use of covers or transversals. So a cover is a subset of your ground set E that intersects every subset you have, that intersects every member. Now, if you give me a whole bunch of disjoint members, they're gonna, each one of them is going to pick at least one point from your cover. So the size of a cover is an upper bound on the size of your packing. So now you can try to minimize the size of a cover, and you get this inequality. On the right side, you get the minimum size of a cover. And on the left side, you get the maximum number of disjoint members of the subsets. All right? And these are 2 different problems. They're dual problems. The problem on the left is referred to as a packing problem, and the problem on the right is referred to as a covering problem. All right? I'm more interested in the packing problem for now. And the left parameter is traditionally called mu of C, nu of C, and the right parameter is traditionally called tau of C. Okay? And this is, and let's just see an example. Let's say the subsets I have are 1, 2, 2, 3, and 3, 3, 1. Okay? If you look at it, I don't have any 2 disjoint members there. Okay? So the left parameter I have is just 1. Okay, so the left parameter I have is just 1. I can only pack 1 member in there. But the minimum size of a cover on the right, I'm going to need at least 2 points to intersect every set. For instance, points 1 and 2 will intersect every set. 1 intersects this set and that set, and 2 intersects then the middle set. All right? And that turns out to be the minimum size of a cover. So the left parameter is 1, and the right parameter is 2. So this shows another thing that I want to point out. You don't always have equality there. All right? So we're going to term those families that give us equality there. We're going to say that my family curly C packs when equality holds there. So there's something really special happening there. Okay? And the theme of the talk is to identify these families that pack. All right? So that's going to be the theme of my talk. Any questions so far about the terminology? All right, perfect. All right, so I said I'm going to be talking about packing odd T-joints. Let me just talk about packing T-joints and do a bit of a survey on the topic. I'm sure most of you are familiar with these things. So you give me a graph on vertices V and edges E, and you give me a subset of the vertices, and you call them terminals. And we have only one requirement on these terminals. You want an even number of terminals. And why you want that will become clear in a bit. So a T-joint is a subset of the edges whose odd degree vertices coincide with the terminals T. Right? It's a bit awkward to define, but That's how it is. And of course, the number of odd degree vertices is always even. So that's why I want T to be even. So if you look at this thing I have here, my 4 odd degree vertices are the square vertices. And the middle vertex, which I have, which is not a terminal, has degree 4, so it's even. So I don't care. So what I have here is a T-joint where T is those 4 vertices. And that's another T-joint. So T-joints don't really have to be connected. So this is another T-joint, as you can check for yourself. Right. And the question is, when does the family of T-joints pact? All right, let's just see. When is it that we can guarantee that the family of T-joints pacts? So when is it that the maximum number of disjoint T-joints, edge-disjoint T-joints, okay? I view T-joints as edge subsets. When is it that the maximum number of disjoint T-joints is equal to the minimum size of a cover? All right? You'll notice that I'm not really defining what the covers are. For now, it's just an abstract thing. It's just a minimum. It's just a subset of edges that intersects every T-joint. So we want to see when is it that we have equality here. All right? So Menger proved in 1927 that if T has size 2, then we always have equality there. So the maximum number of disjoint ST joins, which turns out to be ST paths, is equal to the minimum size of a minimum cover. Okay? So you might wonder, what happens if T has size at least 4? Okay? So let's just look at an example. If you look at this example, so I have 4 terminals and 6 edges. And the size of a minimum cover, you can see that you need, you start a bit and you realize that you need at least 2 edges to intersect every T-joint. And actually, I have a cover of size 2. If you look at the edges incident to this terminal, they're going to form a cover, because every T-joint is going to have an edge incident to each terminal. So that's going to give me a cover of size 2, and that turns out to be the size of a minimum cover. But there is no way you can find 2 disjoint T-joints there. So tau, so nu is 1. So the maximum number of disjoint T-joints is 1. Okay? So if my number of terminals is at least 4, I don't necessarily get equality. And things get more complicated. You could come up with weird examples where you don't get equality. So what are we going to do? So Seymour proved this beautiful result, actually proved a much more general result, but we'll just stick to this, that as long as you exclude this graph that I have here as a minor, as long as you exclude this as a minor, then you get equality. Then the 2 parameters I had there are equal. So my family packs. All right? And when I say minor, I really mean, graph minors. Or in this case, I should say graphed minors. But yeah. But you get the gist. All right, so these are the type of results I'm looking for. So I want to exclude some sort of minor and see if I can get equality or not. All right, so here that minor turns out to be this. And in a sense, this is a tight result because this minor by itself is, that minor doesn't pack itself. So in a sense, in a certain sense, you could actually formulate it in a way so that you get if and only if. But for our purposes, this is enough. But you could criticize this result by just saying that, OK, the minor I have is just too small. It's just got 6 edges. So that gives me a really tiny class. Like most graphs are going to have this minor there. OK, as long as T is at least 4, chances are I'll be able to find that minor. So the minor is too small. What can I do to increase the size of this minor? So I could do that by restricting some parity conditions. And that's what we're going to do. So what if we add a parity condition to the graph we started off with? So actually, you could actually formulate some parity conditions for general families. And it's called an Eulerian condition. So we say a family. So this is a family of subsets that I started off with. We're going to say a family is Eulerian if every minimal cover has the same parity. Now, the reason I have minimal there is to make this property well defined. So because covers, if what you have is a cover, whenever you add a point to it, it's also going to be a cover. So parity conditions wouldn't make sense in that setting. So here I'm just going to say that I want every two minimal covers to have the same parity. And by minimal, I mean inclusion-wise minimal. So what I have is a cover, but any proper subset of it is not a cover. All right? So now I could ask the question, when is it that the family of T-joins, an Eulerian family of T-joins packs? And before doing that, you might ask, what is Euler, because the property I've written down is quite abstract. So what does it mean for a family of T-joins? I could actually recognize that quite easily. It's quite easy to prove that the family of T-joins is Eulerian if and only if every non-terminal vertex has even degree and all the terminals have the same parity. So the terminals either all have even degree or odd degree. Okay? So now I could ask the question, so if you go back to the example which didn't pack, this guy is not Eulerian, because this non-terminal vertex here that I have has odd degree, and even the terminals don't have the same parity. So it's doubly non-Eulerian. All right? So now I could ask, what is the smallest example which I can make, which is Eulerian but doesn't pack? And turns out to be the Petersen. So it's quite big. And there's a conjecture by, well, I'm not going to cite who the conjecture is by, but it roots back to as early as 1981 by Seymour, that says that an Eulerian family of T-joins packs as long as you exclude the Petersen. It's a rooted Petersen, actually. You have the T set there. So you just look at this condition, you look at this theorem, and it's not hard to see that it's just an impossible conjecture. Just because you want to find the Petersen, it's a rooted Petersen, you want to find that as a minor. It's not going to be easy. And we have proof for why it's not easy. Well, the first thing is that it's quite widely known that this implies a four-color theorem, if it's true. If it's true even for planar graphs, it implies a four-color theorem. Which is not surprising, saying that it implies a four-color theorem. And it was proven by Cohen and Lucchesi in 1997 for T up to at most 8. So if the number of terminals is at most 8, you're by default excluding this minor because you need 10 terminals there. And it's true there. So for T up to at most 8, it was proven in 1997 that the conjecture is true. And so actually, it's quite easy to prove this. Okay, any questions so far? Good. All right, so now let's move on to packing odd T-joins. So that's all I wanted to say about packing T-joins. So packing odd T-joins, you just restrict another condition. So we say T-join is odd if it has an odd number of edges. All right? So now I want to pack odd T-joins. So the T-joins I want to pack must have an odd number of edges. All right? So what can we do there? So you can actually formulate this problem in a more general setting of sign graphs, and it's better to consider the problem there just because if you want to define minors respecting parity, sign graphs is a good framework for those. So we're going to formulate these problems in terms of sign graphs. So what is a sign graph? So a sign graph is a pair where the first component I have is a graph, and the second component I have is a subset of the edges called sigma. So here I have the wiggly edges are my edges in sigma, and the solid edges are the other edges. And the wiggly edges I will refer to as odd edges, and the solid edges I will refer to as even edges. Okay? So this sigma tells me what my odd edges are. And I will say that a T-join is odd if it has an odd number of edges in sigma. So if it has an odd number of odd edges. All right? So if you look at this example, this will be an odd T-join. So it's a T-join, first of all. The odd degree vertices are precise of the terminals. And it contains exactly one odd edge, which is odd. And this will be an even T-join. So it's got two odd edges. It's even. All right? So when T is empty, and a minimal odd T-join turns out to be an odd circuit. All right? Now, when these empty odd T-joins become objects that are that you should pay attention to. When you're just talking about T-joins in general, when T is empty, T-joins are circuits, or minimal T-joins are just the empty set. So it's not so interesting to look at the T empty case. But for odd T-joins, when T is empty, they turn out to be odd circuits, so they cannot be empty. So the important case will be T being empty. And then the next step is when T has size 2, a minimal odd T-joint looks is one of two types. So it's either an ST path with an odd number of edges in sigma. So we say that it's an odd ST path. Or it's an even ST path together with an odd circuit. All right? So this is what a minimal T-joint for T being S and T looks like. So these are my minimal odd ST joints. So I can ask the question, when does the family of odd T-joins of a signed graph pack? And again, Seymour answered this question in 1977. You could make 3 examples on 6 edges that do not pack. So actually, the family of odd T-joins for all 6 of them, all 3 of them turn out to be exactly the same. They're just 3 different representations of the same thing. But for each one of them, tau is 2, so the size of a minimum cover, but you can only pack one T-join. All right? So and what Seymour proved was that as long as you exclude these 3 figures, you're guaranteed to have equality. So you're guaranteed to have the maximum number of disjoint odd T-joins is the minimum size of a cover. Okay? So again, we could do the same thing. What if the odd T-joins are Eulerian? Again, the minors we have are too small. They're only on 6 edges. So what if we enforce the property that the odd T-joins are Eulerian? In other words, what happens if we restrict ourselves to those families where every minimal cover has the same parity? And again, you could recognize that quite easily. A family of odd T-joins is Eulerian if and only if. It's quite similar to before. Every non-terminal vertex has even degree. And this time, you want every terminal to have the same degree parity as the cardinality of your sigma, as the number of odd edges you have. Okay. So being Eulerian is quite easily understood. And again, it won't take you long to figure out that none of these 3 are Eulerian. For instance, I think here, every vertex has even degree, but the problem is the terminals have even degree, but I have 3 odd edges. So that won't work. OK, so packing out the T-joins. So packing Eulerian T-joins was already difficult. It implies the four-color theorem, the conjecture you have there. So I'm not even going to try to formulate a conjecture for packing out T-joins. There's already a conjecture out there, but I'm not going to talk about it. So let's focus on small size T. All right? So for T being empty, we're trying to pack odd circuits. This was solved by Geelen and Guenin back in 2002. And what they proved was that an Eulerian family of odd circuits packs if this minor, it's called an odd K5, packs. If this minor is excluded, sorry. If this minor is excluded. You could also try to, some of you may have seen that as being every edge is odd, but they turn out to be the same. All right? And this result by itself implies Guenin's characterization of weakly bipartite graphs. For those of you who are familiar with the result, that was a difficult problem. And this generalized that. So it tells you that packing odd T-joins is not an easy problem, even for T being empty. OK, so what about T of size 2? So remember, we're trying to pack minimal odd ST joins, and minimal odd ST joins are either odd ST paths or an even ST path together with an odd circuit. And what we showed last year with Guenin is that an Eulerian family of odd ST joins packs, as long as you exclude 2 necessary minors. So this is the first one. This is from previously. And this is another one. It looks quite similar to the minors in Seymour's setting, except that you add an edge between S and T. So it's on 7 edges. So this thing is called an odd K5. This thing, you could think of it as the Fano, for those of you familiar with that. OK, so this is what we proved. So as long as you exclude these 2 minors, then you're guaranteed to pack. You might wonder, how is it that I start off with vertices S and T, and I get this guy as a minor? What ends up happening is that you identify S and T along the way. OK, so I'm going to briefly talk about the applications, or the new applications. So it already generalizes T being empty. You could show that it actually generalizes T being empty. It generalizes the integral to commodity flow theorem of Hu and Rothschild and Winston. That's actually quite an easy result. You don't really need this heavy machinery to tackle it. For those of you familiar with fractional packings, this implies that for any edge capacities, I can find a half integral. For any edge capacities, I can find a half integral packing of odd S-disjoints, as long as these two minors are excluded. So there is no Eulerian condition there, but you could see that it's having an effect on the coefficient of my packing. And this by itself implies that there's always a fractional packing of odd S-disjoints as long as these two are excluded, which was a result Guenin proved back in 2002 using Lehmann's theorem, which is heavy machinery. Okay. And there is another application. I'm not going to talk about this too much. Using plane duality, what you could do is you could say that an Eulerian family of covers in a plane sign graph with two outfaces packs, as long as this minor is excluded. But it has applications to packing odd circuit covers and stuff like that. But I'm not going to get into details. But that's what it is. OK, I just want to briefly talk about the proof strategy in the remaining 9 minutes. So again, that's a statement. You have an Eulerian family of odd S-disjoints, and you want to prove that if it packs, if those minors are not present, you pack. So how do we approach this? We prove the contrapositive, first of all. So the proof strategy is we're going to start off with an Eulerian family of odd S-disjoints. And we're going to assume that it doesn't pack. And then what we're going to do is we're going to assume some minimality assumptions, harmless minimality assumptions, to get some added structure to our problem. And then we're going to carefully pick an edge and build one of these two minors on top of that edge. On top of that edge. All right, so let me get more specific. What you do is so let tau be the size of a minimum cover. So you have terminals S and T, and tau is the size of a minimum cover. I want to find tau disjoint odd T joints. OK? Now, the minimality assumption I'm going to make is that I cannot find tau disjoint odd T joints, but for every proper minor of mine packs. So whenever I move to proper minor, that equality holds. Nu is equal to tau. So that's the minimality assumption. Then there are two key claims that run the whole proof. So the first one makes heavy use of the Eulerian condition. And this is the only place where you need the Eulerian condition. So the fact that I cannot find tau disjoint odd S-disjoints tells me that I can find at most tau minus 1 odd S-disjoints. But the fact that I'm Eulerian tells me that I can't even find tau minus 1 disjoint odd S-disjoints. So there is a gap of 2 there. And that's mainly where you use the Eulerian condition. And the reason for that is you say, OK, if I have tau disjoint odd S-disjoints, the parity condition implies that the complement also must contain an odd S-disjoint. That's quite easy. It's quite easy. But that's the main place that you use Eulerian. It just says you don't need to find tau. You find tau minus 1, which makes the problem quite easier. And the second one is it's more of a local property. So you give me an odd S-disjoint, let's call it L. Then what we can show, which is quite easy, is that there is always a cover B, so that B minus L has size at most tau minus 3. So this L takes up too many edges from a cover. And the proof is quite easy. What you do is you delete the edges of your odd S-disjoint. You delete the edges of your odd S-disjoint. And what's left, you have every minimum cover has size at least tau minus 2. You can find tau minus 2 disjoint odd S-disjoints. And those tau minus 2 disjoint odd S-disjoints together with L give me tau minus 1 disjoint odd S-disjoints. And that gives me the contradiction. If you didn't understand this proof, all you need to remember from this is that this cover B gives me a certificate why L doesn't appear in a packing. I know there is not a packing in general, but I need certificates for why these packings don't exist. And for every odd disjoint L, I do have a certificate why there is no packing that contains that odd disjoint L. So you can see why it's quite useful. It's a certificate. It's quite useful. So because it's very useful, I'm going to refer to it as a mate of L. So this cover B is going to be the mate of L. OK, so now let's see how we build the minor. So we first pick an edge omega, which is incident to S, which misses at least one minimum cover. That's just a technicality condition. You can always do it. And then what you do is you contract that edge omega. When you contract that edge omega, the size of a minimum cover stays at least tau because of the way I picked omega. And I'll be able to find tau disjoint odd disjoints. Now I'm going to uncontract omega and see what they look like. So a lot of them are going to be using the edge omega. But because I don't have tau minus one disjoint odd disjoints, that tells me that at least three of them are using edge omega. And then by adding parallel edges, I may assume exactly three of them are using edge omega. So I end up getting an almost packing, basically. I have tau odd disjoints. Here I've represented them as incident sector. I have tau almost disjoint disjoints, odd disjoints. And only three of them are using edge omega. And there's no intersection anywhere else. OK? Now, recall that so let's look at the first three, L1, L2, L3. So each one of them is one of two types, so either an odd ST path or an even ST path together with an odd circuit. So this is going to give you a whole bunch of combinations. Let's just look at two extreme cases. One extreme case is when I have an odd ST, all three of them are odd ST paths, and then the other one is when all three of them are of the second type. So in the first case, this result is going to be very useful. So there is this result independently proven by three people, Seymour, Schrijver, and Thomassen in 1980, which is a linkage type result. So you give me a four-connected graph and four distinct vertices. Then you can either find two vertex external paths, one connecting 1 to 2, one connecting 3 to 4. Or if that's not the case, the graph you have must be planar, and these four vertices must be lying on the outside circuit in this order. So 1 is here, 2 is here, 3 is here, 4 is here. So if you want to connect 1 to 2, 3 to 4, you must meet somewhere in the middle. Actually, what they proved is way more precise than this. It doesn't have the connectivity condition. But to keep it simple, I'm just going to use that version. So this is how we build the minor. I'm not going to tell you how we figure out the parities. It's just too technical. So we start off with edge omega, and we look at the first intersection from the right, and the whole packing, not just those three odd ST joints. Then we build an odd circuit on top of omega. This is not hard. Then what we do is we use Seymour's result, their result, the linkage result, to build a path from here to here and a path from here to here. Disjointness can be proved easily. And then what you do is you use the mates. So each of these guys and every odd ST joint has a mate. Use those mates to construct a path from here to here. And then from here, you can see you have the phono. So what you do is you contract this blue path and this red path, and you get this structure, and you have this blue path. And this turns out to be isomorphic to the thing you start off with. So this is very, very rough, but that's basically how the whole thing goes. In the other case, when you have this, you have three odd circuits here and three even ST paths. What you do is we have this deep technical lemma which gives us a spare even ST path. And this spare even ST path allows us to assume that S is equal to T by means of deletion and contraction, whatever that means. But then when S is equal to T, we fall back into the previous case. So what you do is by Geelen and Guenin in 2002, what they did was they disentangled this odd circuit. You have a lot of intersections. You first disentangle it and make it completely vertex disjoint. Then you use the mates to construct three paths connecting the black one to the green one to the blue one, and the blue one to the black one. And this was that's similar to what Guenin did in 2001 for weakly bipartite graphs. Then Schrijver, I think, is in the room. He has an odd K5 lemma, which is a completely mysterious and beautiful lemma. I still don't understand it to this day. you use that lemma to disentangle these three paths and make him disjoint. Now what you have is an odd K5. So basically that's how the proof goes. So I'm going to end with one open question. Can we extend this result for up to t at most 8? So this is when you don't allow any other minors. So can we extend the result for t up to at most 8? For t equals to 2, it was already quite a lot of work. So I'm not sure how easy it would be. But if someone comes up with a short proof, then it's I don't see why it wouldn't be doable. And that's it. Thanks. Oh, so there's a fourth person who proved it. Or I'll ask you for the name later. Okay. All right. I didn't know that. I didn't know. I just got at first I thought it was only proved by Seymour, but then later I realized Thomassen had proved it, and then I realized someone else had proved it. So I guess there was a fourth person. Okay. It's quite a nice result. Yeah. Thanks.
Any further questions? No? Well, let's set for our next speaker, and thanks again.